Welcome. Today we're starting Unit 7, Quadratic Functions and Equations. We're going to be covering lessons 1, 2, and 3, talking about a different kind of change and sum and product puzzles. Let's start with the bridge. Turn to page 5. We're given a rectangle's perimeter. We want to find the unknown side length, and we want to find the area. So let me highlight what we're looking for. The unknown side length and area. Do you remember how to find area? The formula for area is length times width. Now I'm not going to use x to represent multiplication because we confuse that with variables. So I'm just going to put w in parentheses, put those side by side. We are going to have to find area, but first we're looking at perimeter. So let's slowly highlight what we have been given. What is perimeter? Let's write down that formula as well. Perimeter of a rectangle equals, we have two sides that are opposite. And let me go ahead and put in the label for the opposite side of x centimeters. That opposite side is going to be the same, x centimeters here. And then we have 20 centimeters at the top. At the bottom, we're going to have another 20 centimeters. Opposite sides are congruent. Their measurements are equal. All right, so look at what we have here. We have two of the lengths, the vertical lengths, x. So 2 lengths plus 2 widths. All right, so that's going to be 2 times 20. 2 times 20 plus 2 times, now we don't know this side or this side. We're going to call those x because that's the variable that they gave us. Now that total is going to equal to 120. Now we have an equation. Let's work on solving it. 2 times 20 is 40. 40 plus 2x equals 120. Subtract 40 from both sides. Minus 40 minus 40. This is going to cancel. Bring down the 2x. Bring down your equal. 120 minus 40 is 80. And then finally divide both sides by 2. 2 divided by 2 is 1. That's going to be 1x is equal to 80 divided by 2 is 40. All right, so x is equal to 40. Let's put those measurements here. And let's add all those up just to check. 40 plus 20 is 60. Plus another 40 plus 20. That's another 60. 60 plus 60 is 120. Now that we know the length and the width, multiply those together. 40 times 20, because area is length times width. Four times 2 is 8. And then we have 2 zeros. So 800, area is square units. Our units are centimeters, so our answer is 800 centimeters squared for area. Okay, the unknown side is 40. So there were two parts to that problem. Let's see if we got that right. X is equal to 40, area is equal to 800 square centimeters. All right, let's erase some of this and let's look at the picture that looks like a square. We don't know for certain that it's a square. So let's just not assume it's a square until we find out for sure. All right, the opposite sides, because it says that we have a rectangle. Now a square is a rectangle, but a rectangle is not always a square. We know that opposite sides are congruent. So I'm going to put the measurement 250 meters this time. Okay, and then opposite of the x meter is another x meters. So what do we have here? We have 250 twice. So 250 times 2 plus, that's an x, plus 2x is equal to, this time our perimeter total is 1,000. Now let's solve that equation. 250 times 2 is 500. So 500 plus 2x equals 1,000. Subtract 500 from both sides. 1,000 minus 500 is 500. This cancels here. Bring down the 2x. Bring that down right here. Bring down your equal. And then 1,000 minus 500 is 500. Divide both sides by 2. And 2 over 2 is 1, so that cancels. Bring down your x. X is equal to 500 divided by 2 is 250. All right, so we found the missing side. Now let's look at it again. Okay, the lengths, we can call that length. I'll make a capital L for length. And then our width is W. The length and the width are the same, so all the sides are equal to 250. So that shows that we do have a square. All right, we found the missing width. Now let's find the area. The area is going to be 250 times 250. Okay, 25 times 25 is 625. I would put this in my calculator, not do it in your head. Double check me. And then 2 zeros. So if I did this correctly, our area is 62,500 square units. Let's check our answer. The missing side is 250 and the area is 62,500 square units, and our units are meters. All right, let's go on to the warm-up. We have 3 tables. This is on page 5. So turn in your book to page 5. Look at the patterns in the 3 tables. What do you notice and what do you wonder? Take a minute to look and then come back and see if you got some of the answers that I have. All right, looking at the tables, the x values are all the same. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we're moving up incrementally by 1 each time, starting with 1. The first 2 tables increase. So if you look at the y values and the x values, they're increasing. 0 to 5, 5 to 10, 10 to 15, 15 to 20. It looks like I'm adding 5 each time. So this would be a linear equation because we're adding. First is linear, and table 2 is exponential. So I should be multiplying something to get, multiplying that first y value, which is 3, by something to get 6. 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. 24 times 2 is 48. So 2 is what we're multiplying by each time. Now the last table increases. It goes up from 8 to 11, but then it goes down. Okay, so it increases and decreases. So what we have here is a linear function, an exponential function, and this is going to be something to model a quadratic function, what we're getting into in this unit. Go to page 9, look at the summary and glossary. We want to highlight important information, so read through this carefully. All right, we looked at the relationship between the side length and the area of a rectangle when the perimeter is not changed. If a rectangle has a perimeter of 40 inches, we can represent possible lengths and widths as shown in the table. So you can flip back and see what we had there. We could also consider lengths and widths that are decimal values, such as 6.5 inches and 13.5 inches. For the purpose of looking at relationships between length and width and area, we've chosen to look at the whole number lengths and widths to make it easier for you. Now we know that twice the length and twice the width must equal 40. That's going to be our perimeter, which means that the length plus the width must equal 20. So if we're just adding one length and one width, that's going to be half the perimeter. We've got to double that to go all the way around the rectangle. Now what about the relationship between the side lengths and the area of rectangles with a perimeter of 40 inches? What did you notice? Let's look at these tables. If we have a width of a length of 1 and a width of 19, the area is going to be 1 times 19. If we have a length of 2 and a width of 18, the area is going to be 36. So look at that. Add those together. 19 plus 1 is 20. 18 plus 2 is 20. Remember, the perimeter is 40. So if we've got a length and a width, they have to add up to half of that because we're only going halfway around. So those lengths and widths all add up to 20, giving us a perimeter of 40. Okay, but look at how the areas change. So just take a minute to look at that. Doesn't stay constant, does it? It kind of threw me off because I would think that it would be the same area, but it's not if we change the length and the width. Now here's a graph of the lengths of the areas represented by the table. If we graph those, look at what that looks like. A few things to notice about the relationship shown in the table and the graph. The length can't be 0 inches because a rectangle cannot have a 0 length. The length also cannot be 20 inches because that would make the width of the rectangle 0. Now these points have been plotted with an open circle. Okay, so we've got those points plotted. And the points that we talked about that it cannot be, 0 and 20, we plotted those with an open circle. So make sure that you're seeing that in your book. Now, initially, as the length of the rectangle increases from 0 to 10 inches, the area also increases. Later, however, we go to the highest point on the graph, 10, 100. It starts decreasing. Again, this means that the maximum area on the graph, up here, 10, 100, is where the maximum area of the rectangle occurs. and that's when the length is 10 inches, and the area is 100. We've not studied relationships like this, and we'll investigate them further as we move into this unit. You should do the cool down before you leave class. Okay, if you're absent, make sure that you get the cool downs done. Now we have another table. We have the length in meters and the width in meters, and we're calculating the area in square meters. To calculate area, it's length times width. So 10 times 40 is 400. What is 20 times 30? Use your calculator when you're doing your math, if you can, to check your answers. So 20 times 30 is 600. 25 times 25 is 625. 35 times 15 is 525. And what do we multiply 40 by? Okay, so we have 100 meters. What's half of 100? If we're going all the way around the rectangle, okay, it would be 100. Half of that would be 50. So a length plus a width, that's how they're getting these two numbers, two whole numbers that add to 50. 40 plus 10, 20 plus 30, 25 plus 25, those all add to 50. So what do we add to 40 to get 50? We're going to be adding 10. So 40 times 10 is 400 again. So notice how it starts out going up till we get to the peak, and then it starts going back down again. If the values for the length and area are plotted, what would the graph look like? So think about what we saw in that previous graph. The points would form a stretched out upside down U shape or an arch. Let me go back. It's going to look like this. This is what a quadratic equation looks like. A quadratic equation is an equation that has an exponent. The highest exponent is a power 2. How is the relationship between length and area of the rectangle different from other kinds of relationships we've seen before? Write down what you remember about our exponential and our linear functions. How is this different? As one quantity increases, the other quantity first increases and then decreases, instead of always increasing or always decreasing. Our linear and our exponential functions always increased or decreased, but this will change. It'll go up and then back down, or down and then back up. All right, let's look at this bridge on page 216. We want to look at all expressions that are equal to 10 minus 2x. What I'm going to do is I'm going to take these expressions and I'm going to distribute multiplication of 2 into each term inside the parentheses. So I'll start multiplying 2 times 5. That's going to give me 10 minus 2 times x. Now look carefully. Does that match this? 10 minus 2x? That looks exactly the same. So I'm going to circle that as being equivalent to 10 minus 2x. Let me distribute the 10 into both terms. We're going to be multiplying 10 times 1 and 10 times 2. 10 times 1 is 10. Put that minus sign down, and then 10 times 2 is 20. Don't forget we're multiplying it by 2x, so this is going to be 20x. Now that does not look like this, so I'm going to mark that one out. Let's distribute the negative 2 to the 5. Negative 2 times positive 5 is negative 10. And then negative 2 times negative x is a positive 2x. Now this looks similar, except the signs are different. They're opposite. So this is not a match. Now last, let's distribute the negative 2, multiply that to the x, and then negative 2 multiplied to negative 5. So that's going to give us negative 2x, and then negative 2 times negative 5 is a positive 10. Now let's compare this to our original expression. Okay, 10, this is a positive 10 and a negative 2x, positive 10, negative 2x. So this is equal. We just have the two terms switched around. Let's check and see if we got that right. 10 minus 2x is 2 times 5 minus x. We got that one. And negative 2 times x minus 5. We got both of those. All right, look at the warm-up on page 16. Claire was learning how to use a bow and arrow. The graph shows the height of the arrow as a function of time since she released it. Time is going to be on our x-axis, so we start at 0 and we go up to 2 seconds. And we're counting in increments of a quarter of a second, I believe. All right, and then the height, we're going from 0 to 2, 4, 6, 8. Notice how we're counting our height in feet on the y-axis. Use the graph to identify each of the following. Be prepared to share your reasoning. I'm still getting some answers in the cool downs where you get an answer, but you're not explaining. Even in the homework, if it says explain, you're missing more than half of the points by not explaining your reasoning. So let's practice now. At what height did Claire release the arrow? So that's going to be our y-intercept. It looks like she released it at 4 feet. What was the maximum height of the arrow? So the peak of this graph is going to be at, it's really hard for me to see. Let me count, 2, 4, 6, 8, 10, 12, 14, 16, 18. Maximum height is going to be at 18 feet. Maybe you should look in your book. It's saying it's a little bit above that. It's saying it's at 19, but I'm going to change this. I think it's at 18. I don't have the book, so make sure you're looking in your book to make sure that you see what I see. Now, when did the arrow hit the ground? So it was launched at 4 feet. It goes up to 18 feet, and it hits the ground at 2 seconds. Turn to page 17. Let's complete activity 1. What price to charge? We have a company that sells movies online, and it's deciding how much to charge customers to download a new movie. Based on data from previous sales, the company predicts that they charge X dollars for each download. Then the number of downloads in thousands is 18 minus X. So they've already given you the equation, the expression, and how to find the revenue in thousands of dollars. Okay, now let's look at the first example. Okay, price in dollars is 3. So we're going to substitute 3 for X. So 18 minus 3 gives us this 15. Okay. Now we're going to multiply 3 times 15 to get the revenue. How much is made when we sell that in thousands of dollars? Okay. The number of downloads. So we have 15,000 times 3 is 45,000. So let's go to the next one. 5, we're going to replace the X with 5. So 18 minus 5 is 13. And then the revenue in thousands is 5 times 13, or 65,000. Going down to that third row, 18 minus 10 is 8. 10 times 8 is 80,000. Let's go down to the fourth row. 18 minus 12 is 6. And 6 times 12 is $72,000. Now look at what's happening. We started at 45,000, went up to 65,000, 80,000. Now we're going back down. What do you think is going to happen here? Okay, I predict that it's going to go down. Let's see if that's if that's actually what's going to happen. Replace the x with 15. 18 minus 15 is 3. 3 times 15 is 45. It did go down. One more. 18 minus 18 is 0. And 0 times 18 is 0. All right, now let's look at that pattern, what we're doing here. So we have a value, we're going to call it x. Okay, so 18, we subtract x from 18, and then we're multiplying those two together to get x times 18 minus x. And we're asked in question number 2 to write an equation for the revenue R as a function of the price per download. We already have the expression. Let's just write that as an equation. So the revenue R equals x times 18 minus x. Now you're asked to verify that 1456 is a solution to the equation, and you're asked to show your work and explain what this tells us about the solution. Okay, so a sample response. Okay, we have 1456. 14 is your x, 56 is your y. Now, we're going to verify that because we're going to put 14 for x. So there's an x here and 14 for x here. Where does that y go? Where does the 56 go? The y always is your output, so it's going to go where the revenue is. So 56 should equal to 14 times 18 minus 14. We perform, I may have said that and confused you, but we're going to perform the order of operations and do the parentheses first. What is 18 minus 14? 18 minus 14 is 4. We're going to multiply that times the x that's on the outside. Okay, and x is 14. 14 times 4 equals 56. Okay, we're showing the work down here. So we substitute in the x and y values into our expression to verify that that is a point that's going to be on our graph. This means that if the company charges $14 per download, that's your x, your input is x, and your output, the revenue predicted, is to be around $56,000. All right, on page 20, in this lesson we explored different representations of a quadratic function. Now, there were still some questions about what a quadratic function was. Quadratic function is a function that has a squared term in it, but no terms higher than a squared term. Okay, so we're looking for that squared term. Linear equation, we're adding or subtracting an amount, but it only has x to the first power. So these are quadratic functions. They have a squared term. This one up here, x times 10 minus x, if you distribute that x, you have 10x minus x squared. So we do have a squared term. So this is a quadratic. The graph of the equation is shown here. And using the graph, we can see that the horizontal intercepts are at 0, 0 and 10, 0. This means that if the price per order is $0 or $10, the company makes no money. We can also see that 5.25, let's go over here to 5 and go up to 25. That's our maximum. That's the maximum amount that we can get in dollars. If we charge $5 per order, the maximum revenue is $2,500, because right here on the left-hand side, our key says the numbers, the Y's, are hundreds of dollars. So we have a quadratic expression. Quadratic expressions are written in the form of ax squared plus bx plus c, where a is not equal to 0, meaning we have to have a squared term. So a quadratic function is a function where the output is given by a quadratic expression in the input. A quadratic expression has a squared term. All right, let's do the cool down. A company charges X dollars for tickets to a concert. The number of tickets sold in thousands depends on the price of the ticket and can be expressed by 32 minus X. Write an equation to represent the revenue as a function of the ticket price X. Okay, so the revenue R is equal to X. That's the price per ticket times 32 minus X. Now you can distribute that and you can write it as 32X minus X times X is X squared. Now you're asked, is the point 7, 175 on the graph of the equation? So let this be your X and let this be your Y. Okay. And if you're just guessing and you say yes, that's not going to be enough. Okay. Because the answer is yes, it's on the graph. But tell me how you know that. It's because it's a solution to this equation. Okay, this expression right here, or this equation right here, substitute in 7 for X and 175 for Y. Then simplify that equation and you'll see that when you distribute this or you subtract 7 from 32 and then multiply by 7, you get 175. All right, turn to page 29 and continue going through the lesson summary and glossary. We've seen that the graphs of quadratic functions can curve upward. Graphs of exponential functions with bases larger than 1 also curve upward. To compare the two, let's look at the quadratic expression 3n squared and the exponential expression 2 to the n. We have a table of values for n. We're going up by 1, 1, 2, 3, 4, 5, 6, 7, 8. And we calculate when we input n what 3n squared is. 1 squared is 1 times 3 is 3. 2 squared is 4 times 3 is 12, and so forth. Now 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, 2 to the fourth power is 16, and so forth. Now compare these two functions. We start off with the output for the exponential, or the quadratic, being larger than the exponential function. Still larger when n is 3, still larger when n is 4, and 5, and 6, and 7, and 8. Do you notice anything else? I said n7. 147 is larger than 128, but I also said n8. Is 192 larger than 256? No, this is where it starts going down. So exponential functions go up or down. Quadratics, okay, with a squared term, are going to curve, so they're going to change direction. They'll have a maximum or a minimum, and then they'll start changing direction. All right, we also saw an explanation for why exponential growth eventually overtakes quadratic growth. When n increases by 1, the exponential expression 2 to the n always increases by a factor of 2. So exponential equations are always increasing when we have a growth factor bigger than 1. The quadratic expression 3n squared increases by different factors depending on n, but these factors get smaller. For example, when n increases from 2 to 3, let's look at that. The factor is 27 over 12, or in decimal form, 2.25. When it increases from 6 to 7, the factor is 147 over 108. Remember how we found that growth factor? We go from this number and we divide it by this number. Okay, that's about 1.36. As n increases to larger and larger values, 3n squared grows by a factor that gets closer and closer to 1. A quantity that always doubles will eventually overtake a quantity growing by this smaller factor at each step. All right, the practice is on page 12, 1, 3, 5, and 6. Page 21 is where it starts, 1, 2, 3, and 7, and page 30, 1, 2, 4, and 6. Make sure that you complete your cool downs in Canvas and your practice in your workbook, and then transfer your answers into Canvas.